In section 2, we're going to be talking about how a solution is formed, essentially, looking at how different rates help things to dissolve better, the idea of like dissolves like, and the idea of how temperature and pressure will affect a substance's solubility. So first off, the factors affecting the rate of dissolution. Different ways to speed up the dissolution process would be if we can increase the surface area of the solid. For instance, if I had a cube of sugar and I decided to crush it up into granules, the granules are going to dissolve much easier because more of the surface of the sugar is being in contact with the solvent, which is water. Stirring or shaking, we know, obviously, is going to increase those interactions between the molecules of the solute and the solvent. And also higher temperatures. When you have, for instance, tea is going to mix with the water at a much higher rate if the water is warmer versus if the water is cooler. You can see this with food coloring. It's going to disperse a lot faster in higher temperature water than it would with cold temperature water. So with solubility, eventually you are going to be adding so much material, so much solute that you can't dissolve anymore. There becomes a point where you're going to have some of the sugar settling out of the bottom no matter how much you stir it, and you reach a limit of how much solute can dissolve. And this depends on several things. It depends on the nature of the solute, the nature of the solvent, and the temperature. We can actually increase a substance's solubility by increasing its temperature, meaning we can allow it to dissolve more substance. So just so you can see it with the particle model, solubility, we see that lithium chloride will in fact dissolve in water because all those water molecules will surround the chloride ions and the lithium ions, whereas with the insoluble solvent toluene, the lithium chloride does not dissolve. We don't see those molecules surrounding the different ions. So again, we talked about this with the factors that help to increase solubility. And we have those interactions between the molecules. And when the maximum solubility is reached, the molecules are essentially returning to solid form at the same rate at which they're dissolving. So it's not like you just have a clump that didn't dissolve. Some of it's redissolving, but then at the same rate, some of the stuff that was dissolved is turning back into solid, crystallizing, if you have a solid in a liquid. So in this case, solution equilibrium is the physical state in which those opposing processes of dissolution and crystallization are happening at the same rate. When we do reach that maximum and the solute cannot be dissolved anymore, we have what's called a saturated solution. So at this point, no more solid can be dissolved. And this equilibrium has been established because the ions are both leaving and entering the solid phase at the same rate. Anytime that we haven't reached this point, we call that solution unsaturated. It hasn't been saturated to the point where nothing can dissolve. We can still add more sugar, for instance. It will keep dissolving. Any solution that's not saturated is going to be considered to be unsaturated. And you can see how that works on the graph. If I have a mass of NaCH3COO added to water, the more I add, the more will be dissolved. And once I hit this point at about, it looks like 40 maybe 45, 40, a little less than 45, I hit this point where, oh, it says right here, solubility is 46.4 grams per 100 grams. That means that I can dissolve 46.4 grams effectively of sodium acetate in 100 grams of water. At that point, it becomes saturated. And at that point, the more and more that I add, it does not dissolve. And you can see crystals starting to form at the bottom of the container. There is a way to manipulate the solution in terms of temperature so that you can actually dissolve more solute than would normally be dissolved. And this is called supersaturated solution. So what I have to do is I heat up the solution, I increase the temperature. This in effect increases how much can be dissolved. And so I can add more and dissolve more at a higher temperature than I would have been able to at the lower temperature. So what happens is if I continue to cool this solution down, it's going to crystallize. The solute is going to crystallize, and that's how we can effectively make crystals in the lab. So again, every solution has a particular solubility. Solubility is the amount that's required to form a saturated solution. In our example here with sugar, we can dissolve 204 grams per every 100 grams of water. And note that the temperatures required there, the 20 degrees Celsius, because different temperatures are going to allow for different solubilities. These are things we have to determine experimentally because solubilities of solutions do vary quite a bit. And we can also, because these have been found experimentally, we can look in different chemical handbooks to find the solubilities per 100 grams of solvent at a given temperature. So here's some different ions that are soluble in water, but there are exceptions that once they contain the other ion, makes them insoluble. So you can see that list there: ammonium, potassium, sodium, acetate, chlorate, chloride, nitrate, sulfate, all soluble in water. But the exceptions with acetate, if I have an iron 3 or an aluminum ion added to that acetate, they will no longer dissolve in water. They will actually stay together and become insoluble. Same with if I had, for instance, silver chloride would not dissolve even though sodium chloride would. So then on the other hand, we have some common ions that are insoluble in water, like carbonate, hydroxide, oxide, phosphate, silicate, sulfite, until I add certain ions to those. For instance, potassium carbonate would dissolve. If I had sodium carbonate, it would dissolve. But anything else with carbonate, other than these exceptions, would be considered insoluble, meaning it doesn't dissolve. So we have a rough rule for whether or not one substance will dissolve in another. We say like dissolves like, meaning we're looking at the type of bonding, if they have similar bonds, if they have similar polarities, looking at the intermolecular forces between the solute and the solvent. So typically polar substances will dissolve other polar substances, and nonpolar substances will dissolve other nonpolar substances. For example, if you have a whiteboard and you write on the whiteboard with Sharpie, you might have a little scare that you just ruined your whiteboard because that Sharpie won't come off with water. because water is polar, but will not dissolve the Sharpie. So what you can do, because the Sharpie ink and dry erase ink are both nonpolar, if you actually write over the Sharpie with dry erase marker, it'll come pretty much right off. And that's why we don't usually wash clothes and things with water alone. We usually put a soap in there because water is considered the universal solvent. It dissolves many things. Because it's polar, it's not as effective as dissolving nonpolar.